Okay, so today we're going to learn about derivatives. And to put it plainly, a derivative is a tool that is used to find the slope of a function. And you might ask, why is that so special? You've been doing slope for so long already. And I think the best way to explain that is through an example. So let me make a XY graph. Actually, yeah, sure, XY graph. Um, and yeah, let's just say that there is a function y is equal to 2x. So on this graph, it's going to look something like this. And it'll just keep going. And if I ask you to find the slope at x is equal to 1, I think mostly you could do that. You just find the rise over run. So the rise here is 2, right? 2 in the y direction. And then the run is 1 in the x direction. And all of you know the slope formula, which is change of y over change in x, which is exactly what's happening here. So the final value that we end at is 4. The initial value for the y is 2. And then we do the same thing for the x. The final is 2. And the initial is 1. And then we get 2 over 1. So our slope is 2. And yeah, this seems pretty simple. And this method works on any function where the slope does not change in that interval. So, for example, here, right, in the interval of, let's just say from 0 to 4, we could take the slope anywhere here because the slope of this function does not change. It's a straight line. And this is true even if the function itself changes, right? Let's say that there's a function like this now. We'll just say that it's y is equal to 1/2 x. So within the interval of wherever this is, so let's say it's 2.5 right here, 2.5 to however long this function goes on to the right, you could take the slope using this method. But now, let's say that there's another function. And this function is a function that all of you are familiar with. It's the quadratic function. So, so y is equal to x squared. So with this quadratic function, we'll just plot the points. 1 squared is just 1, and then 2 squared is 4. It goes up like this, and then it'll just keep going up. So yeah, it curves, right? If you could look at the graph, it's not a linear graph anymore. So yeah, now what happens if we try to find the slope at 1? How would we do that? Because if we use the same method as what we did here, we could just do the rise over the run. So what happens if we do something like this again? So the rise is this and the run is this, right? And yeah, the rise here is supposed to be equal to 4 because 2 squared. So it's 4 and then 1. So does that mean that the slope here at this point is 4? No, it's not. Because if you see, the slope looks something more like this at this point. And this function, it obviously does not have a slope of 4. It has a slope less than 4. Because if there's a function at this point that has a slope of 4, that means that the function would be going this steeply. Because you'd be going 1 and then 4. As you move over 1, you rise 4 in y. But so this is the function that we get, the blue function, when we do just the normal rise over run method that we did here. But we could tell visually that the slope is not the blue one at x is equal to 1. It's the purple line. So this is where the concept of a derivative has to come in. A derivative finds the slope of a function of a function even if it's curved. So even if the slope of that function changes in that interval, you can find it. So if you could see the slope from 0 to 3, it changes throughout the whole thing. So now, how can we come up with the concept of a derivative? So what we could do is we could take the y value, right? Or, okay, let's start with this. Let's say that we take some x value. Let's say it's just an x value here. So it could just be x equals 1 or something. And then we move over h far away. So we move, this is h here. So h is just however far this distance is from this x value. So what we could do is, if we want to find the change in x here, then we could model that by doing this. So x plus h, right? Because this is the distance, the final distance that we have. And then we can do the initial distance, which is right here. So the final distance was right here that we moved, and then the initial distance was the green. And the initial distance is just the x value that we started with. And then now we could do the same thing with the y value. So how do we find the final y value that we end at? The way that we find that is just plugging into the function. So we just do f of x plus h, and then our initial y value, we do the same thing. We just plug it into the function, f of x. So this is exactly what we did here. So if you would do this method with this initial example that we had, you would get the same answer too, right? Because here our final point was x is equal to 2, and our initial point was 1. That means our h was 1 because we moved over a distance of 1 here. So now, how do we find the slope here? The way that we do that is we keep decreasing h, the value h, all pretty much as close as we can to 0, because we want the slope to continue to come down to match what this is. So the blue function, as h gets closer, will look more something like this, right? And then it will start to look even more like that. It will keep coming down and down and down, and then eventually it's going to get super close to the purple function, which is the slope that we actually want. Okay, so what tool can we use to do that? The tool that we could use is the limit. So if we take the limit of this entire function, I need more space. Let me go down. Yeah, so let's take the limit of this entire function. So the limit as h, we'll talk about what h has to go to later. So f of x plus h minus f of x over x plus h minus x. Okay, so in order for this to get closer and closer, that means h has to go closer and closer to 0. The distance that the x travels has to be closer and closer to 0. So that means this should try to approach 0. So then now, this is the fundamental definition of what a derivative is that most calculus students will get introduced to. So if we use this method and we plug in the function that we have, what will we get? So the function y, which is the same thing as f of x, we'll plug that in now, okay? So our input here is x plus h, so then we just plug that into for x. So then now we get x plus h squared plus, this should be a minus, and then the input here is another x. Just I don't want to get into functions, but this here is just an input. And then here is also a placeholder for the actual input. That's why this replaces that. Okay, so it's just another x squared. And then, yeah. And then here is its own function. We don't have to do anything with this. Okay. So then now the best thing that we could do is try to simplify. So here, the x's cancel. Let me use another color. So the x's cancel. And here we should factor. So when we factor, we get, let me just write this real quick. We get x squared plus 2xh plus h squared. This turns into this. It's just polynomial factorization. And then there's an h on the bottom. So on the top, these cancel. And now we could factor further. Yeah, we could get h in front, and then we get 2x plus h, and then an h on the bottom. So then now the h's cancel out. So what we're left with is the limit as h goes to 0 of the function 2x plus h. And then since it's going to 0, we could just replace h with 0, and then we get 2x. So this is the derivative of the function x squared. And the notation that is used to write that is the derivative dy dx of the function x squared is equal to 2x. And we could test that above, whether it's true or not. So whenever we use the idea of a limit, the delta y and delta x here that we had before turns into dy and dx because we use the idea of a limit, and it's like an abstract idea that we have to change this to dy dx to show that we're using infinities here. We're getting infinitely close to 0. And then a question that some of you might be wondering is, why can we cancel these h's? Back in pre-calculus, you learned that whenever there is a 0 on the bottom, something happens. The function doesn't exist, or there's a hole. A hole happens whenever the variables cancel. The variable on the bottom that is 0 cancels out with the variable on the top. So this is exactly what happened. So does this mean that the function is undefined at h is equal to 0? And yes, this actually does mean that the function is undefined at h is equal to 0. But we have to remember we are using a limit. So we are not actually going to h is equal to 0. We're getting infinitely close. So even though this function here is undefined at h is equal to 0, it doesn't mean that we don't get anything out of it. We get something out of it because we're using the concept that we're getting infinitely close, not actually being at 0. Okay, enough of that. So then now let's test whether this idea works. So the derivative, which is the slope at every single x point in x here, is described with this function. So let's test if that idea works. Okay, this function is a little messy. Let me make a new one real quick. Okay, so then we just use the same function. Y is equal to x squared. And yeah, so then now the derivative dy dx is equal to 2x. So then let's see what value we get whenever we plug in 1 for x. So what is dy dx, or the slope at x is equal to 1? We get just we get a line that looks like this. It's a slope of 2. Yeah. So if you see, it does match what the curve looks like at x is equal to 1. Because whenever we plug in 1 here, we get 2. But we have to keep in mind 2 represents the slope. So we go here, that means we rise 2. So we go from 1 and then we go up to 3. So yeah, the change in y is 2 and the run is 1. What happens if we plug in 2 in for x here? Then we get 4. So if we draw that out, we are somewhere here. And then the slope will be even steeper. It'll look something like this now, which matches what it is for x is equal to 2. Yeah, it might be a little confusing at first why if we plug in 2 in for x. Let me just write out, I guess, the notation of what it would be. So it's like plugging in 2, because this is a function it's in itself, then the output is 4, right? After we plug in 2 in for x. And it might be a little confusing at first what 4 means, but 4 is the slope. Just the same concept as exactly what we did here. We get 2 as its slope, and then that's why we could describe this function. Yeah, same thing here. 4 is just the slope at the value 2. X is equal to 2. Okay, yeah, so I guess a quick summary. This method this dy dx only works, the change in y over change in x only works whenever it's a linear function where the slope does not change in that interval. If the slope does change in that interval, which is what happens in a quadratic function, we have to use the concept of a derivative. And the concept of the derivative also works with linear functions, so you could try it yourself. If you plug this in and then you go through the steps of what happened here, you'll get the same thing. You'll get a slope of 2. Okay, yeah, thank you.